Hello students, I am Dr. Nimi Singh. Today I bring you a learning module in BSc Forensic Science on behalf of the content writers Dr. GSOD and Ms. Tulika Banerjee on an important unit of forensic ballistics, which is examination of firearm part 1, in which we will discuss about history of forensic identification system, the rifling types and their identification, the types of chambers, basic methodology used in comparison microscope. We will wind up this module with a discussion on mathematical proof in striation matching. Let us start our module with a look at what we are going to learn today. As with any other evolving science, the exact origin of forensic firearm identification is covered in anonymity. It is hard to decipher as to exactly what the first fired bullets from a given firearm comprised. A specific number of impressed grooves having equal spacing, all of them inclined in the same direction and same angle, and that they are probably same on every other bullet being projected from the same firearm. In the same way, it can never be inferred upon that when the subsequent steps was followed in comparing the width of grooves, the number and the degree of inclination with those from firearm of a different make. Now, the next step, however, required a quantum leap in lateral thinking to show that all bullets fired through the same weapon bore microscopic stria, parallel impressed lines, which was unique to the weapon from which they were fired. Now, early cases of bullet identification were in June 1900, an article appeared in the Buffalo Medical Journal by Dr. A.L. Hall to the effect that bullets fired through different makes and types of weapon of the same caliber were impressed with rifling marks of varying type. The riots in the year 1907 in Brownsville, Texas, saw the staff of Frankfurt Arsenal being employed with the task of identifying the firearms from which firing took place because of being open fired by members of U.S. infantry. Now, as a method of identification, magnified photographs of the firing pin impressions on the cartridge cases were used. The examiners concluded from the recovered bullets that they contained no distinguishing features or markings in relation with the particular firearm from which they had been fired. Now, use of photomicrographs. This work got recognition in 1912 when Victor Bellstad made the next profound advancement into this science. Now, Bellstad, in an attempt to identify the firearm from which the bullet has been fired, took photomicrographs of lands and grooves formed on the bullet because of the rifling present in the barrel of the firearm. On examining those micrographs, he came to the conclusion that the cutter employed for producing rifling within the barrel of the firearm will never leave exactly the same markings in the subsequent excursions through the barrel. Now, these markings, which by inference must be unique to that barrel, are then imprinted as a series of striations on any bullet passing through that barrel. He thus reasoned that it is possible to identify beyond reasonable doubt that a fired bullet originated from the barrel of a certain weapon and none other. Work by Bellstad, although extended beyond matching of striations on bullet and also comprised of comparison of markings present on the fire cartridge cases in self-loading pistols. Now, the markings he identified as being those bearing identifiable stria and markings unique to a certain weapon. For those caused by the firing pin, breech phase, cartridge extractor and ejector. Now, he reasoned that the final pass made by a cutting or finishing tool in, for example, the cartridge extractor left a series of striations which were unique to that extractor. Pierre Medlinger mentioned the reproduction of minute irregularities in the breech face of the soft brass of American primers. Now, early use of comparison microscope. Philip O. Greville was the first to realize the use of comparison microscope for forensic comparison of stria on bullets and cartridge cases. Spencer Lens Company manufactured the first commercial comparison microscope, followed by Bosch and Lomb and Leeds. For the first time, evidence based on comparison microscope was presented to the court of law in the United Kingdom. In the infamous case of murder of Constable George William Guttridge. Now, brief facts of the case were that of a fired revolver cartridge case was recovered from the motor car used by assassins of Guttridge. After several months of effort, the police were convinced that two men, Brown and Kennedy, were the culprits. Now, two revolvers were found in the possession of Brown, and the whole case got dangled on a single question, that whether one of these was a murder weapon. Eventually, by the help of comparison of striation marks, it was established that one of the revolvers did in fact fire the cartridge, and after a long trial, Brown and Kennedy were executed for the heinous crime. Binocular comparison microscope. The next major improvement was the introduction of the binocular eyepieces. It may, however, be noted that this does not give stereoscopic images, as each stage still only had a single objective lens. It barely made operational use of the instrument much more comfortable. It is often claimed that two-dimensional photographic reproduction of striation comparison do not represent the three-dimensional views obtained from the eyepieces in two dimensions, as a single objective lens used in comparison microscope is incapable of representing three-dimensional vision. Thus, there was some truth in the statement that a photographic representation of striation matches was of little evidential use. Photography of stria. Now, while most comparison microscopes have some form of photographic system for recording the striation marks, this is only of any real use in tool mark examination, since stria present on flat surface may easily be photographed, but striation on bullets are on the circumference of a curved surface, and only a small portion of this can be adequately represented in focus of a single photograph. However, modern instruments are now attached with a closed circuit television (CCTV) and a monitor connected to an additional video recording device. Now, with this type of assembling, it is now possible to record the striation marks around the whole circumference of a bullet. Rifles, revolvers, self-loading pistols and most single-shot pistols have rifled barrels. Shotguns are generally smooth-bore, although some older weapons were provided with a short length of rifling at the muzzle end for use when firing solid slugs. Now, this system of rifling was called paradox rifling. Some of the more modern shotguns specifically designed for firing shotgun slugs are also found with rifling. Now, this can either be a short section of rifling at the muzzle end, similar to the old paradox rifling, or rifle down the whole length of the barrel. Now, these are sometimes referred to as slug barrels. Rifling consists of a series of spiral grooves which are cut into the inside surface of the bore of the barrel and are there to impart a spin to the bullet through its longitudinal axis. The gyroscopic motion of the bullet helps in the stability during its flight, thereby preventing it from tumbling and losing its accuracy. Rifling within the barrel of a firearm comprises of a raised up portion called as land and the depressed portion called as grooves. Now, the grooves are the depressions which are cut away by the rifle cutter, whereas the lands are those regions within the barrel which does not come in contact with the rifling cutter and are left as raised up portions. Twist of rifling is defined as the number of inches of the barrel needed to form one complete twist. For most modern weapons, this is consistent throughout the barrel's length. The actual degree of the twist cut within the barrel of a firearm is calculated in accordance with the bore of firearm, length, velocity, weight and the density of the intended bullet. The actual degree of twist is critical. If it is too high, the bullet will become unstable, thereby having a consequential loss in its accuracy and too little the spin. The bullet will lose the stability and will start to tumble end over end. Now, older weapons often had a gain in twist in which the rate of twist increased from breech to muzzle. This was done so that the soft lead bullets could have a grip on the rifling because of the high rate of acceleration provided by the black powder propellants. Rifling can have either the right hand twist or the left hand twist, both having as such no advantage over one another. Now, the number of groups cut into barrel can range from 1 to 24 or even more in what are called micro grooved barrels. Once again, the difference in 5 and 24 groove rifling seems to be more academic than practical. The class characteristics. Now, when talking about rifling, each firearm will consist of similar resembling features being present in all firearms of the same make and model. Now, these features are also known as the class characteristics and comprise of the number of lands and grooves, the direction of twist, the inclination of twist and width. By simply measuring the number, width and degree of rotation of the rifle grooves on a bullet, it is actually possible with a fairly high degree of accuracy to determine which make and model of weapon it was fired from. The spiral grooves present within the barrel of a firearm is there to provide a gyroscopic motion, that is a swift spin of the bullet on longitudinal axis. Now, this effect helps in stabilization of the bullet, thereby preventing it from tumbling or yawing and hence improving its accuracy. The types of chambers. In modern firearms, the various types of chambers present consist of annular, ringed, fluted, perforated and helical chambers and are helpful in the identification of both the individual as well as class characteristics. And the main types of chamber markings encountered are as follows. Fluted chamber. Fluted chambers are longitudinal flutes which are deeper at the front end of the chamber and taper off towards the rear. Now, these allow the gases produced on firing to blow back the outside of the cartridge case during firing. Now, this counters the internal pressure and lubricates the case, thus facilitating the extraction process. Now, this is utilized in blowback and delayed blowback weapons, where pressures are relatively high, thus making extraction difficult. Now, scoop flutes. Now, these are generally wider than those in normal fluted chamber and are deep in the middle, tapering off to nothing at each end. The pressure produced on firing flow from the case into these depressions, thus retarding the extraction process. This type is mainly utilized in low pressure blowback self-loading pistols. Helical flutes. Now, these are similar to longitudinal flutes in their manner of operation and are designed to assist extraction. This type is only seen in low pressure blowback self-loading pistols. Annular rings. Now, these can be anywhere along the length of the chamber and are quite shallow. Once again, these are designed to retard the extraction process via flow forming of the cartridge case into the depression. Perforations. These are mainly seen in 0.22 caliber self-loading pistols, whereas the perforations are designed to slow down the extraction of the cartridge. Now, oversized chambers, the German FG-42, Paratroop Rifle 42 and some issues of the MP-44 make use of the same principle as a fluted chamber, in that they have chambers that permit escape of gases around the cartridge case. Now, these chambers, however, are not conventionally fluted, but are of larger diameter for approximately the rear half of the chamber. This allows the gases to escape into this area, thus equalizing the pressure and easing extraction. Now, the depth of the impression which is left on fired cartridge cases varies enormously, with longitudinal flutes leaving the most significant markings and the helical almost none at all, other than the slight blackening of the discharge residue. Class characteristics. Rifling of each weapon will possess a series of family resemblance which will be present in all the weapons of the same make and model, correctly called class characteristics. They relate to the number of lands and grooves, their direction of twist, the inclination of twist and width. Whilst these dimensions can be extremely useful in identifying the caliber, make and model of the weapon which fired a particular bullet, they cannot be used to individualize the weapon. Individual characteristics. Whilst all weapons of the same make and model will have the same class characteristics statistically and empirically, it can be shown that no two weapons will have exactly the same individual rifling characteristics. These individual characteristics are caused by small defects in the rifling which are produced during the manufacturing process. They are totally random and as such are as individual to a particular weapon as fingerprints are to a person. These marks are called individual characteristics. It is thought by many that the individual characteristics in a weapon's rifling result from the actual cutter which makes the rifling. Whilst the actual cutter does veer very slightly with each pass it makes, and factors such as inclusions in the metal of the barrel and swath build-up do produce individual characteristics. This is not the primary source of the marks used when individualizing a weapon. The marks inside a barrel which characterize that weapon are not longitudinal as produced by rifling cutters, but are rotational or spiral. These rotational marks are produced during the initial drilling and reaming of the weapon's bore, and as such are totally random. They result from wear of the drilling tool, build-up of swath on the cutting edge and hard inclusions in the metal's crystalline structure. Being rotational, they leave far more characteristic marks on a bullet passing over them than longitudinal striations. It is the rotational or spiral marks on the barrel's lance which translate into longitudinal striations on the grooves of a bullet as it passes down the bore. And it is these striations which enable a fire bullet to be connected beyond a reasonable doubt to a particular weapon, whilst the majority of these individual characteristics will remain with the weapon for its working life. The bore of a weapon will also acquire additional individual characteristics as it ages. Now, these additional marks can include, for example, small corrosion pits, damage caused by improper use of a cleaning rod, and accidental damage to the muzzle. Overzealous cleaning with abrasives and steel wire brushes to remove metal fouling can also damage or alter the appearance of a weapon's individual characteristics. In some instances, the excessive use of force can actually erase some of the individual characteristics. It can thus be seen that the individual characteristics in the bore of a weapon are constantly evolving. Obtaining control samples. When a weapon has been located, it will be necessary to recover control samples of bullets and cartridge cases for comparison with those recovered from the crime scene. Now, before the firearm is being fired, it is required that the excess of oil, grease or debris should be wiped off from within the barrel, because presence of any of these will result in formation of additional striation marks on the fired bullet. In case of self-loading pistols, it is necessary to clean any grease debris from the standing breech face, because it may act as a cushion, resulting in the prevention of transference of striation onto the head of cartridge case. In addition, the first round fired could impress the debris into the standing breech face with sufficient force so as to leave marks which would be reproduced during subsequent firings. A point to be noted here is that before any grease or debris is being removed off from the breech face, it should be examined well under the microscope, because there is often an imprint of debris or oil on the head of the last cartridge to be fired. After carefully cleaning the weapon, a minimum of 4, preferably more rounds of ammunition of exactly the same make and type should be fired, and the components are collected for examination. These rounds should be collected in sequence, as there could be a progressive change in the barrel due to the rusting or some other factor which could affect the striation comparison. It is extremely important that exactly the same type and make of the ammunition to be used, as minor variations in the hardness of components or pressure produced could seriously affect the appearance of the impressed stria. The bullets should then be cross-compared until a mental picture is obtained as to what are the salient features and what marks can be disregarded. Recovery methods for fired bullets. Now, if a weapon has been recovered, it will be necessary to compare fired ammunition from this weapon with fired ammunition recovered from the scene. Obtaining a series of test cartridge cases from a self-loading pistol presents little difficulty, as they merely have to be picked up. Obtaining fired bullets in a near pristine condition is, however, a little more difficult. In the past, cotton waste or wadding has been used, but this material can be quite abrasive to soft lead bullets, especially those of 0.22 inch rimfire caliber. High grade long fiber cotton wool is extremely good at preserving the finest stria on the softest of lead bullets. It is, however, very expensive and has to be frequently replaced. Vertical and horizontal water tanks for bullet recovery are currently very popular, but these also have their own problems. One of the major problems faced with all water recovery tanks is that of algae formation. The nitrates in gunshot residues, they form an ideal breeding ground for algae, and the tank soon becomes a thick green soup. Whilst this does not affect the bullet recovery, it is not a pleasant medium to work with. Bleach or a bactericide can be used to remove these algae, but great care must be taken to ensure that the bullet surface is not corroded by whatever is added to the water. Horizontal bullet recovery tanks, whereas the bullet is fired at an angle from one end into the top of the tank, suffer from bullet recovery problems. Once the bullet loses its velocity, it drops to the bottom of the tank. Locating the bullet is another problem, as the formation of algae can make it very difficult to find the bullet in the first place. One problem which all water recovery tanks suffer from is the propensity for the bullet to spiral down the tank, eventually hitting the sides and becoming damaged. This problem is for some unknown reason particularly acute with vertical tanks. This is a difficult subject to comprehend due to the statistics involved. As such, it is often, when dealing with the questions on the subject in court, glossed over with such comments such as statistically it can be shown, but as I am not a statistician or empirical studies have shown, or even a match is one which exceeds the best known non Stria individuality. It is possible, however, to use a very simplified approach and to obtain an idea of the probabilities of grooves on bullets from different sources having corresponding stria. If, to simplify the matter, as far as possible, we take an analogy of randomly filling a number of boxes, so that the analogy can be translated into matching striations in a rifling groove. There will be three conditions. There are 20 boxes, 10 of which will be randomly filled. Each of the filled boxes can be heavily shaded or lightly shaded. Each of the filled boxes can have either an X or a Y. Taking condition 1 alone, in this condition there are 20 boxes, 10 of which are randomly filled. Now, the chance that in a similar 20 boxes exactly the same combination will be filled is given by the standard statistical formula, and the formula is C raised to power m n. Now, this is equal to m factorial upon n factorial into m minus n factorial, where C is equal to chance of stria accidentally matching, n raised to power m C is nothing but a chance of accidentally matching stria within the parameters m and n. M is the number of boxes, n is the number of filled boxes. Factorial, that is 5 factorial is equal to 5 into 4 into 3 into 2 into 1. Now, for this example, if m is equal to 20, so n is 10. Then putting the value in the above equation, we get C20n 10, which is equal to 20 factorial upon 10 factorial into 20 minus 10 factorial, that is 10 factorial. Now, this will come out to be 1,84,756. Thus, the chance of having two sets of 20 boxes each having 10 randomly filled boxes. In the same combination is a chance of 1 in 1,84,756. Now, if we now take into consideration condition number 2, in addition to the condition number 1, condition 2 states that each of the filled boxes can be lightly shaded or heavily shaded. As each box has one of the two possible shadings, the chance that the first box will be same in both the sets is 1:2. The chance that the second box is the same will also be 1:2. But as this is dependent upon the first box, the chance that the first two boxes will be shaded exactly the same is 1:2 into 1:2, for example 2:2. Thus, the chance of all 10 filled boxes in both sets having the same shade of filling is 10 raised to 2 raised to power 10, which is equal to 1024. The chance of 10 randomly filled boxes out of 20, each with randomly chosen dark or light shading, is therefore 1,84,756 into 1024, which will come out to be 18,91,90,144. The chance of two sets of 20 boxes, each with randomly matching 10 filled boxes which are either light or dark shading, is a chance of 1 in 18,91,90,144. If we now take into consideration condition 3 in addition to the conditions 1 and 2, condition 3. Now, if each of these shaded boxes can then have either an X or a Y, the same probability factor as above is relevant, that is 2 raised to power 10. Thus, the figure becomes as shown on the screen. The chance of two sets of 20 boxes with 10 boxes randomly filled with either light or dark shading and either an X or a Y is a chance of 1 in the figure which has been shown on your screen now. If now we place this into the context of a bullet, we have a single groove on a bullet which we divide into 20 longitudinal sections, and in 10 of these longitudinal sections are randomly placed 10 striations. The chance of two grooves on bullets from different weapons accidentally matching is thus chance of 1:184,756. If each of these striations can have one of two profiles, for example, a pointed shape or a square shape, then the chance of two grooves from different weapons accidentally matching under these criteria is 1,84,756 into 1084, which comes out to be a number given on your screen. That is a chance of 1 in the number on your screen. Now, if each of these striations can now be one of two widths, say thick or thin, then the chance of two grooves from two different weapons accidentally matching under all the three criteria is going to be the figure which is shown on your screen. That is a chance of 1 in the figure which you have just now seen. That is, of course, taking a very simple case, but in reality there will be not just 20 possible positions for striations in a groove, but hundreds. There will be just 10 striations, but once again hundreds, the number only being limited by the resolving power of the microscope. There will not be just two profiles, but tens of possibilities, and the width once again will be tens of possibilities. Just taking one groove alone, the number becomes so vast that it must approach infinity. If this is extended to the possibility of finding two bullets where the entire grooves match, then the number must be infinitely large and reach a stage where it is beyond the realms of possibility. It can then be seen that the chance of finding a complete set of accidentally matching stria in bullets from different sources is so infinitesimally small as to negligible. Now, this statement is just as viable for other impressed striation marks as it is for the striations found within the rifling of bullets. It thus follows that the pattern of surface contours comprised of peaks, ridges and furrows found within an impressed tool mark can be considered unique to that tool. It is immaterial whether the tool is the standing breech face of a weapon or a firing pin, the tip of a pry bar or the faces of a bolt cutter, for the marks produced will be individual to that tool. Firearms found at the scene of crime needs to be identified and compared to determine whether the specific crime has been committed by that particular firearm only or not. For the purpose of identification and comparison, some prominent features are looked in, for which helps in concluding the same. Features include both the class as well as individual characteristics of cartridge case and bullet, which helps in forensic firearm identification. Now, my dear students, hope you have enjoyed this learning session, and if you want more information regarding the topic, you can visit our website, that is www.cec.nic.in. Till then, keep studying. Goodbye.